Okay, I hope you can see that. So I've worked on matrix factorizations for a number of years. That's a topic in commutative algebra and algebraic geometry. It's closely related to topological quantum field theories. And topological quantum field theories themselves are quite closely related, as some of you may know, to quantum error correcting codes. So there's a kind of 1 degree of separation between these topics, but there are some new and maybe interesting direct links between them, and I want to speak about one of those today. So actually my interest in this topic comes in some roundabout way from my interest in logic, and I'll start by saying a little bit about that, but this is mainly for context and motivation. Technically it won't play much of a role, that is, logic won't play much of a role in this talk beyond the next few sentences. So an important conceptual insight from modern logic is that there is an interesting dynamical process lying behind, in some sense, function composition. I'll just give a brief example. If you have two functions which are computed by some algorithms, then the combination of those two algorithms, you might think of plugging the output of one Turing machine as the input to another Turing machine, for example, is itself an algorithm, but often that can be simplified. So this is technically called cut elimination or normalization.
Recording in progress.
In logic. And this is a very it's one of the most interesting parts of logic and computer science, theoretical computer science, is the study of this process of computation. But we don't really have a good mathematical understanding of what this process is in some abstract way. So what I'm going to say here is that as mathematicians, that is, say, as algebraic topologists or algebraic geometers, taking our cue from the logicians, we perhaps ought to look for, I'll call it, subatomic structure. Inside the seemingly atomic operation of composition. So you could think of your favorite category, right? Or bicategory, in which a composable pair maps to its composition, and this process is sort of like a one-step thing. There's nothing inside, usually, this map here. Depending on the context, maybe it's quite a complicated operation, but at the formal level, we don't tend to put extra structure inside this operation. So I want to talk today about an example in which such structure can be found and appears quite natural. So example, of such structure in the context of hypersurface singularities. Okay, so the talk's going to be about a certain bicategory that encapsulates hypersurface singularities and some kind of correspondence between them, and some interesting internal structure to the composition operation in that bicategory. And then I'll show you how that structure, which appears quite naturally but maybe seems a bit disconnected from anything else, is in fact closely related to quantum error correcting codes, a bit surprisingly. So that's the plan for the talk. So I'm going to begin by saying a little bit about matrix factorizations. I don't assume you've seen this before. Some of you may have. So let K be a commutative ring. You could assume it's a field without losing anything here. We single out a special kind of polynomial so kx underlined for me is going to mean some polynomial ring. And we call a polynomial a potential. And this, the sort of approach I'm taking here is from the theory of Landau-Ginzburg models in string theory. This is where the habit of calling this thing a potential comes from. So we call it a potential if the partial derivatives form a quasi-regular sequence. If you know what a regular sequence is, a quasi-regular sequence is just a slight weakening of that. The Jacobi ring, so the coordinate ring of the critical locus of W, is a finitely generated free K module. And thirdly, the sequence is what's called causal regular. This actually implies the first condition, but it appears more technical, so this is sometimes called causal regularity. The causal complex of the partial derivatives of W is exact except in degree 0. And as I just said out loud, actually 3 implies 1. So really you could take 2 and 3 here. Maybe that seems a bit technical, and it is. It's necessary for the general setting of commutative rings to set it up in this way. But if I just take a complex polynomial and I want to know a sufficient and useful condition for it to be a potential, you can just ask that the critical points, the points where all the partial derivatives of W vanish, this set of points is isolated, that it's 0-dimensional. And that's enough. Okay, so e.g. any isolated hypersurface singularity. Okay, so these are the basic objects we're interested in, these isolated hypersurface singularities, or this slightly more general, this more general class of potentials. Associated to such a potential is a category, a triangulated category of what are called matrix factorizations. These were introduced by Eisenbud in the 80s, and I'm going to give you the definition. You could think of these as modules over the hypersurface singularity, or sort of like the analog of the bounded derived category as a triangulated category that captures the geometric content of this object, the object being the germ of this hypersurface singularity at a point. These have been extensively studied over the last few decades. They were studied also extensively in the 80s when they were introduced in commutative algebra. But over the last few decades, particularly in connection with string theory, because these objects naturally arise there. So matrix factorization of MF, or MF, of a potential W is a Z2 graded free KX module, possibly of infinite rank. So to say it's Z2 graded says that it comes as an even and an odd piece. And this Z2 graded free module comes equipped with a KX linear map dx of degree 0, which satisfies the condition that it squares to multiplication by W. So matrix factorization is a square root of a polynomial, right? In the same sense that you can square root Laplacians. That's perhaps the earliest example of a matrix factorization, Dirac's example of square roots of the Laplacian using Clifford algebras. And in fact, matrix factorizations of quadratic forms are basically the same thing as representations of the Clifford algebra of that form. So you can think of the theory of matrix factorizations as an extension of the theory of Clifford algebras beyond quadratic forms. Right? Of course, you can't associate a bilinear form to a polynomial of higher degree than 2 in some useful way. But this is kind of the replacement theory. This can be made precise using A-infinity algebras and so on. But that's not what I'm going to talk about today. So this operator dx can be, if you like, written in blockwise fashion as a pair of matrices A and B, and they satisfy this condition. Okay, so a matrix factorization is a simple object. It's a matrix of polynomials satisfying this constraint. A morphism of matrix factorizations is just something like a chain map. So it's a kx linear map of degree 0. Oh, I meant to say degree 1 here, right? If you look at this matrix here, it sends x1 to x0. It's an odd map, or a degree 1 map. So a morphism is a kx linear map of degree 0 such that dyf is equal to f dx. So there's a natural notion of homotopy on such morphisms, defined entirely analogously to morphisms of chain maps and their homotopies. I won't spell it out, but given that, you can define a homotopy category of these objects, and that's the next topic I want to discuss. Okay, so here are some triangulated categories. Associated to a potential. The definition, you'll notice, makes sense for any polynomial. I don't need it to be a potential. And similarly for what I'm about to say, you get triangulated categories for any polynomial, but they're well-behaved triangulated categories in some sense. For example, they're Calabi-Yau in the case of potentials. Okay, so I'll start with the biggest one. So this is a triangulated category of all, let's say, homotopy category of all matrix factorizations, all meaning including those of infinite rank. So a matrix factorization is a Z2 graded free module. It could be infinite rank or finite rank. In T, I take all matrix factorizations, and hence the capital HMF. H for homotopy, M for matrix, F for factorization. This is a triangulated category with arbitrary coproducts. Inside it are the compact objects. I'll say a bit more about those in a moment. Let me write S for lowercase HMF, and this means the homotopy category of finite matrix factorizations. Now, this isn't the set of compact objects for a kind of standard reason. It's not closed under summands. So clearly S is contained in T, but inside T it's not closed under summands. So if I just add in all summands, so I take the thick closure of all finite rank matrix factorizations, I get the set of compact objects inside T. I don't have time here to give you examples but it's even in the simplest singularities you can come up with examples of natural objects which have some ends that are not actually finite rank. You can't split the idempotent in the finite rank category, at least over polynomials. And there's a bit of a technical point, but I want to remark on it at this stage, which is I can formally take the idempotent completion of S so I denote by S omega the idempotent completion, so this is the universal idempotent complete K-linear category into which S maps, sometimes called the Karoubi hull. And that thing is equivalent to what I'm writing with this plus here. Okay, so this will come up a bit later. This relationship between these two ways of thinking about completing HMF. You can either, I mean, they're identical in some sense up to equivalence. You can either formally add splittings of idempotents, or you can literally add them by going to infinite rank. And those are the two possibilities you see here. Okay, so associated to any potential, we have these various triangulated categories. And with this on the board, I can define a bicategory, so a sort of weak 2 category. The bicategory LGK has potentials as objects, and I need to specify a Hom category. The Hom category, that is the 1 morphisms and 2 morphisms, from a potential W to a potential V, are given by matrix factorizations of the difference. So the difference of two potentials is itself a potential. So I take here the ring with both sets of variables, and I take the difference between them, and then I take the idempotent completion somehow. I'm going to take it by taking some ands within the capital HMF for this definition. Okay, so I don't have time to spend a lot of time explaining how this bicategory works, but I hope the general picture makes some sense. So the objects are, say, isolated hypersurface singularities, if you think of a potential as being such a thing, and the 1 morphisms between isolated hypersurface singularities are something like bimodules or correspondences or Fourier-Mukai kernels. That's how you should interpret these objects in HMF of V minus W. Okay. All right, so this is the key player in the story I want to tell about composition. Are there any questions at this point? I haven't told you what composition is in this bicategory. I'll be a bit more specific about that in a moment. Okay. So I'll just enumerate some important theorems about this bicategory, and then so I've got a picture here of a stratified 2-manifold, which is the kind of TQFT picture on what this object is about. But let me state a sort of Coverall Theorem which encompasses work by quite a few people. So this bicategory has a lot of nice properties. So maybe I should say that this was first studied by mathematical physicists, Lazaroyo and McNamee, and then by Kovanov and Rosansky. So in their paper on Kovanov-Rosansky homology of knots and links, this is the key kind of mathematical object. And then it's been studied by a few people since then. Okay, so this bicategory has left and right adjoints for all one morphisms, and up to shifts they're isomorphic. So the upshot of the next few statements is this bicategory has lots of duals, all possible duals. It has adjoints for one morphisms, it has adjoints for objects. So this is a result of myself and Niels Carquil, a mathematical physicist, from a while ago. It's a symmetric monoidal category, bicategory, with duals. So it has duals for objects. And in fact, every object is fully dualizable. So this is a one-object tricategory, if you like, LGK. So this is due to Niels and a student of his, Montoya. And it's also, pivotality is sort of buried in the previous one a bit, but it's also what's called a super bicategory. So there's a Z2 grading floating around everywhere. The home categories are matrix factorizations with these kind of Z2 graded objects. And so there's associated parity shifts at the level of everything inside the bicategory, so it's what's called a super bicategory. And some of the relevant structure there was worked out by myself and a student of mine, Jackson Godfrey. Okay, so it's an interesting bicategory made up of these hypersurface singularities. Now the picture on the left is what you can do with a bicategory with this kind of structure. So if you have a category or a bicategory or a higher category with certain kinds of structure, you can associate to such categories TQFTs of various kinds. To this particular bicategory, you can associate at least, depending how you view it, one group of people would call it a 2-1 defect TQFT. So it's a gadget that can evaluate Bordisms that look like this. So this is a stratified two-manifold of a particular kind. The one strata or the two strata are labeled by objects of LG, and the one strata are labeled by one morphisms. And so this particular diagram here would evaluate to a one morphism from kind of, if you read this plane up here, that's the identity object in the bicategory, and you would read this as a composition that goes to the identity object in the bicategory. And the identity object is the potential zero. So maybe just for the sake of a bit of color, this Bordism evaluates to a one morphism from the potential zero over the polynomial ring with no variables to the potential zero. And such one morphisms are Z2 graded vector spaces. Okay, so this thing evaluates to a Z2 graded vector space. The construction of Coverall-Theorem homology is a bit similar. So with a bit more structure, they draw diagrams of a similar kind that evaluate to not invariance. Okay, so at a general level, that's all I want to say about LG. Now I want to zoom into its composition operation and start to explain what I mean by looking inside that operation for additional structure. And partly this is an invitation to you to find other examples of a similar kind, because I think they must exist. It's just this is the only example that I know sufficiently well to see how this works. Okay, so let's talk about composition. And I'm going to draw a fairly large diagram here. Given potentials, W in the variables x, V in the variables y, and U in the variables z, start down here. So how do we compose in this bicategory? Well, we want to take a y in here, that is a matrix factorization of u minus v, and an x in here, which is a matrix factorization of v minus w, and we want to get out something which is a one morphism from w to u. Okay, well, this category here is HMF of k x z u minus w. This here is by definition a similar thing. Okay, well, let's sit all this inside capital HMF. Let me just drop the rings and write it like this. Well, there is a perfectly good composition functor that takes the pair yx and maps it to the pair which tenses. Remember, these are modules, right? So y is a module over this ring and x is a module over that ring, and I can just tensor them over the common variable y. The differential is just the usual differential on a tensor product. You can check that's a matrix factorization of u minus w, so no problem. It's a little bit less obvious, but still not too difficult to check that in fact this is definitely an infinite rank matrix factorization over kxz, because the y variables have disappeared, right? So essentially you're asking for kxyz as a free module over kxz. That's infinite rank. But you can prove that up to homotopy equivalence actually let's say lives in here. That object, which is an infinite rank matrix factorization, is a summand of something finite rank. Okay, so that's how this composition is defined. You take a pair, you get this tensor product, and then you just observe that the image is actually in here. Okay, that's fine. Except it's not very finite, right? And it's not very explicit. It leaves you wondering whether you could actually ever compute the composition of a pair of one morphisms in this thing. And well, that just leaves you in exactly the same situation you are if you're talking about Fourier-Mukai transforms, right? If you compose Fourier-Mukai transforms between bounded derived categories of smooth projective varieties, say, you know that composition is, well, you take the functors associated to two Fourier-Mukai kernels and you compose the functors. You know that's the functor associated to the convolution of those two kernels, but that convolution has a derived push forward in it that you may not be able to compute in practice, right? So it's a highly non-trivial operation, and also here. So if I ask for a composition that looks like this, it's not surprising. I mean, I could ask for a composition that just goes straight from here to here. Right, takes in two finite rank things and gives me a finite rank thing. You could ask if that exists. What you actually get is a map that lands here. And of course this sits inside here. Okay, so what this diagram's trying to get at is maybe it's hopeless to expect some closed formula that just gives you the output of composing two one-morphisms in this bicategory without going via some infinite rank thing. To just write down the answer directly is probably impossible. But maybe it's not impossible to still ask for a finite description in some sense, right? Maybe it's not actually writing down a matrix factorization. Maybe it's some other kind of data. But it's not completely hopeless, and in fact you can do it. It's not hopeless to write down some kind of finite datum which represents this composition in some useful way. And that's what I call the cut, and that's the next thing I want to tell you about. So the cut is going to be some kind of replacement for this composition, which is more computable, more effective, more finite. Okay. Maybe before I define the cut, let me just tie this back briefly to the topic introduced at the beginning of trying to find some internal structure to the composition. So suppose you wanted to get a finite answer out of this composition as it stands. What would you have to do? That is, finding a finite rank representative for the composition in the bicategory, which is this tensor product. So here's what you'd have to do. You can write down the tensor product. So here's a matrix of polynomials with x, y, and z in it. You have to invert the following equivalence. So the equivalence I'm talking about is related to this arrow blue, in blue here. So as I mentioned earlier, the Karoubi completion is equivalent to the other completion. So they might seem like, well, what's the difference? But one is completely finite and the other isn't. So remember, that thing lived inside HMF. And the way we define it, the tensor product, or the composition of the one morphisms, lives in this category. It's an infinite rank matrix factorization, which we know is up to homotopy a sum end of a finite rank one. We know these categories are equivalent. To give an object here which maps to this up to isomorphism, what are the objects in the Karoubi completion? Well, they're finite rank matrix factorizations together with an idempotent E. So E is a map from Z to Z, and E squared is E. That's just some matrix of polynomials. So this is a completely finite datum. Whereas this is finite if you write it over the ring with the y's in it, but strictly speaking, written in this guy here, here it's, you could say it's finite or infinite depending on your taste. Okay, so 3, you have to perform the following kind of operation. You have to look at Z, and you have to split that idempotent, right? So here's the idempotent. Fg is 1, Gf is E. Let me draw this kind of separating line here between the finite rank and the infinite rank world. So we have this idempotent. The fact that it corresponds under this equivalence to y tensor x is exactly to say that one way to split this idempotent is to take this infinite rank thing. That's what this says, right? Now it may be that that idempotent actually splits in HMF without the omega, right? It may be that there exists a splitting, let's call it lowercase f, lowercase g, and let me refer to it as y star x, say, just to have some different notation. So if we had fg as 1 and gf is e, we would have these two different splittings of the same idempotent, this one and this one, and therefore they have to be equivalent. So if you could, in the completely finite world, actually split this idempotent, which often you can, say on the computer, then you've computed a finite rank representative for that composition in the bicategory. Call it y star x. So that's what it takes to actually compute the composition in this bicategory. And you can look at this picture and kind of wonder whether this is a hint of something more systematic, some kind of more systematic structure that refines the composition. It's not quite that on its own, but it's a hint of something. And that something has to do with Clifford algebras and what I call the Clifford thickening. And that's the topic that I'm moved to now. But are there any questions about these two boards before I move on? We're teaching an introductory algebraic geometry class in this kind of game environment at the moment, so there's some students doing exercises there. Okay, so here's another way of thinking about this convolution of kernels or composition of matrix factorizations as one morphisms. It involves developing a bit more theory about supercategories. So maybe I'll say what a supercategory is, first of all. So a supercategory, or a Z2 graded category, is a category T, k-linear. Everything is k-linear here, and a functor f from t to t, and a natural isomorphism between f squared and the identity functor on t, satisfying some conditions. I won't go into it. Any of those HMF categories or capital HMF is a supercategory where the functor f takes a matrix factorization to its shift by 1, which is defined in the same way as for complexes. You just shift all the objects, so the things from even degree to odd degree, and you change the sign on the differential. Now I want to talk about, so there's a deep role for Clifford algebras, as I mentioned already in the theory of matrix factorizations. Matrix factorizations of quadratic forms are the same thing as representations of a Clifford algebra. But what I'm about to explain is a kind of second way that Clifford algebras enter the story. And for that I need to just tell you a particular kind of Clifford algebra, and I'm going to call them Cn. So if you haven't thought about Clifford algebras, let me just tell you some generators and relations. So let Cn denote the algebra so it's a Z2 graded algebra, associative algebra, non-commutative, generated by 2n symbols. I call them gamma 1 through gamma n, and gamma 1 dagger through gamma n dagger. This notation is from the physicists, so this is annihilation and creation operators. They call these canonical anti-commutation relations. We say it's the Clifford algebra of a kind of T plus T star with a canonical evaluation pairing. So these are generators of odd degree in the algebra, and they satisfy, as I said, canonical anti-commutation relations. Okay, so all the things anti-commute except for these pairs here. So I need to tell you some examples of modules and bimodules over these algebras. So this is a series of algebras. C0 is just the ring K. So for Sn, I'm going to mean the spinor representation. So this is the exterior algebra on n symbols. This is a left C module. With gamma I acting as contraction with the one form theta I star, and gamma I dagger as wedging. Okay, so I think you're all familiar with the commutation relations between those operators of wedge product and contraction, and you'll verify that those are exactly these relations. And in fact, mapping an element of Cn to this action on the left is an isomorphism between Cn and the endomorphism ring of Sn. Okay, so this is a Morita trivial algebra. It seems a little strange to introduce it as a crucial object, but you'll kind of understand, I hope, why. Okay, so Sn is a left Cn module, and I can also consider what I'll call Smn, which is the canonical bimodule between Cm and Cn, and it just has this structure. Right, so here's the defining kind of representation of Cn. If I dualize it, I get a right Cn module, and then I just tensor it with Sm, which is the canonical module for Cm, and this is a bimodule. Again, not a very interesting bimodule. Okay, so these are Clifford algebras, or series of Clifford algebras, and their basic modules and bimodules. And out of this, I'm going to build something I call the Clifford thickening of any supercategory. So let T be a supercategory, for example, a category of matrix factorizations, which is idempotent complete. The Clifford thickening, well, this is what I call it. It's very likely this has appeared somewhere that I'm just not aware of, so if you know another name for this, please let me know. The Clifford thickening, I'll write it as T bullet of T. There's a fancy way of describing it. It's the Grothendieck construction applied to a certain pseudo-functor. I'll just tell you in more down-to-earth terms what it is. So it has as objects tuples x, n row, where x is an object of T, n is an integer, and rho is a left Cn module structure on X. Now you might wonder how I define a tensor product like this, but X belongs to a k-linear category T, And Cn is a free k-module of some rank, so that tensor product just means take a bunch of direct sums of x with itself and its shifts. Now, I've got various n's here, right? So this is not Cn modules in T for a fixed n. I allow all possible n's. So that means I have to define morphisms, and this is where if you've seen a growth and deconstruction, you recognize the trick here. So a morphism between such tuples it's a morphism of Cm modules so there's a canonical way of turning X into an Cm module, right? Because this is a Cm-Cn bimodule, and X is a left Cn module, so I can just form this tensor product, and then I can ask for a Cm module map from that tensor product to Y. And then you can compose those things in a reasonably obvious way. So that's a category, the Clifford thickening. It's a bit of an odd construction because Cn is a Morita trivial algebra. So T is equivalent to the Clifford thickening. So it's really the same category, but not quite. I mean, it's equivalent, but that doesn't mean it's the same. Okay, so let me explain what I mean. There's a functor from any idempotent complete supercategory to its Clifford thickening, which sends an object to itself with the action of C0. C0, the Clifford algebra with no generators, is just K. And just the identity on X is a K-module structure on X. And this functor is an equivalence of categories. Now I want to explain why. I mean, it's ultimately because Cn is Morita trivial, but it's worth spelling it out a bit. So, since Cn is Morita trivial, if I give you a Cn module, X, in T, there exists some X tilde in T and an isomorphism So if you've spent some time studying Clifford algebras and their modules, sometimes people call this a coefficient space, right? If you have one of these Clifford algebras where, I mean, everything is the spinor representation tensored with some vector space, right? And it's similar here, just for the same reason. So every Cn module is the spinor representation, this exterior algebra, tensored with something, some object of T. Call it the coefficient space or coefficient module. And that's the reason why this functor is an equivalence. Because this isomorphism itself, if you unpack what it means, it's an isomorphism of this guy with no Clifford algebra acting, with X itself with Cn acting in the Clifford thickening. Okay, so what's the point of introducing the Clifford thickening? Well, it may be possible to specify specifying objects here can be easier I mean, we saw an example earlier where we had the Karoubi completion of HMF and this plus completion, where even though they're equivalent categories, finding a representative for a given object in the other category may be highly non-trivial. Right? You could think about bounded-derived complexes of infinite dimensional vector spaces with finite dimensional cohomology and finite dimensional vector spaces. Okay, you write down the cochain complex which computes singular cohomology of a compact space. That doesn't mean you know a finite rank representative for that thing, right? So it can be a very different proposition to specify objects in equivalent categories, and it's similar here. So I'm going to show you in a moment in the context of LG how sometimes it's much easier to specify an object in the thickening than it is in T. And then somehow finding this x tilde, this coefficient space, is kind of a secondary step. Okay. Yep. All right. So just give me one moment. So I'm going to define for you what I call the cut operation, which instead of taking values in HMF, takes values in HMF bullet in this thickening. And that can be specified completely finitely. And then I'll hopefully be able to tell you in an example what code that corresponds to in the sense of quantum codes. So that's the plan. Okay, so definition. Given one morphisms Y, I'll just say from, so these are between potentials, so from V to U, and from W to V. The cut is a finite rank matrix factorization. So I take the original tensor product, but I mod out by the action of the Jacobi ring, or the Jacobi ideal of the intermediate variable. By hypothesis, the Jacobi ring is finite rank free over K, so that's why this ends up being a finite rank free matrix, a finite rank object over that ring. The differential is just the sort of induced one from the tensor product. And this has an action of Cm. So Cm, M is the number of variables in this intermediate ring where the V comes from. And Cm acts by a family of operators, gamma 1 through gamma m, gamma 1 dagger through gamma m dagger. So these are odd morphisms of matrix factorizations which satisfy the Clifford algebra relations up to homotopy, and they're given by somewhat complicated formulas. I'll just sketch them briefly. So these are non-trivial objects. They arise from perturbation theory applied to the causal complex on the partial derivatives. So the way to compute them is to take a commutator of a pair of operators on this numerator here. One is just the sum of the differentials, and the other is a differential operator, so to speak, which differentiates in the direction of the partial derivative themselves. So this is not a variable, but nonetheless you can make sense of something like a connection which differentiates in these directions. So this would be the normal directions to the critical locus, if indeed that were a manifold, but it's not in general. So these are what are called Atiyah classes. And the gamma daggers are sort of themselves expressions in similar objects. So you differentiate the differential on x, and then there's some terms also involving Atiyah classes. So this commutator is defined on here and passes to the quotient, as you can check. So it doesn't really matter too much for the purposes of today what these operators are, but this is sort of where some real work enters the story, constructing these operators. Okay, so that's a definition. The cut is some object. It's got some Clifford algebra representation. The theorem says that this thing is the same as the composition. So a theorem, there is an isomorphism in the homotopy category of CM modules between this thing with the action I just described and SM tensored over K with this tensor product. And the Clifford algebra action on the right hand side is the canonical one. Okay, so this says that this here is this tilde, so to speak. And that's an infinite rank thing, so it's not like you want to extract that from this thing, but as I sort of sketched earlier, you can use the Clifford algebra action here to find this coefficient module, which, if you're working in finite rank things, will be finite, and that will be equivalent to the tensor product. Okay, so this means that this, with its CM action, is isomorphic to the tensor product in the thickening. Okay, and in fact, you can set up a bicategorical version of this, which is equivalent to LG. Okay, so this cut operation realizes the idea earlier that maybe we couldn't define the tensor product or a finite rank representative directly, that is, specify something in HMF, which is finite. But in this kind of slightly different category, the thickening, you can write down, I just did it on the previous board, it's explicit in terms of formulas. You can explicitly write down a finite rank object, this matrix factorization, the cut, together with this Clifford action, which represents the composition in a completely finite way. And okay, so I'm going to now take a few minutes to tell you what happens in a simple example and how codes arise. Okay, so the simplest possible example you might compute this cut operation in is the following. You could take xn squared, just in kxn. That's an isolated hypersurface singularity, a zero-dimensional one. So these are objects in LG, and what I'm drawing here is a bunch of one morphisms. And you can just take the identity one morphisms between all these. So these are basically the same object, right? So this is just composing the identity one morphism on this very simple object x squared in LG with itself n minus 1 times. Okay, so these guys here, these are just the identity one morphisms, and as matrix factorizations, Z2 graded free modules, you can realize them in the following way, as exterior algebras tensored with a polynomial ring. And the differential is this thing here. Okay, so I said that to compose these in LG, one way to do it is to compute the cut. So the cut would be, I stick all these things together, and I've got, for every variable in between, I get a Clifford operator. So say associated to xn minus 1, I'll have a gamma and gamma dagger. And associated to xn minus 2, I'll have some other gamma and gamma dagger. But let me just focus on the Clifford structure on this cut that comes from this last intermediate variable here. So if you tensor all these exterior algebras together, and remember that taking the cut means modding out by I, and I here would, so in this final cut here, I'm going to mod out by I, and I is generated by dxn minus 1 of xn minus 1 squared. So that's just going to, this operation of modding out by I will just send xn minus 1 to 0. So you can easily compute that this just has the final variables left in it, and it has the exterior algebra in all these psi's that are the underlying modules of the diagonal of these deltas. Okay, and what are these Clifford operators in this case? Well, gamma works out to be the following, as you can compute from those formulas with a bit of practice. This is the case of a quadratic form, so everything's pretty straightforward. Okay, so this is the formula. These are operators on the cut, right? They're operators on this thing here. And what I'm writing down is, well, this here you should read as contraction with that one form, and this here you should read as wedge product on the left with that one form. It's actually a typo. Okay. So, well, how are we supposed to... We know what composition is. You're composing identity one morphisms with itself. So the answer should be the identity one morphism again. So we're not looking for the answer so much as the method to produce the answer. Okay, so here's what the earlier prescription would say we should do. So we should take this cut. We've got, in particular, gamma and gamma dagger. And then we should find this coefficient module, which corresponds to splitting the idempotent gamma gamma dagger. That's an idempotent if you think about the exterior algebra, because you're adding in some generator, some odd generator, and then contracting with it, so you get back down to sort of the identity. But you can check that's the same as taking the kernel of gamma, or the image of gamma dagger, whichever one. Now that splits off something to do with the first cut here, and then you have something to do with the second cut, and so on. So you can keep going in this way. And eventually you'll get down to compute a finite rank representative for the composition. Okay, so what is the kernel of gamma? Well, to cut us a bit of a long story short, if you just look at that formula and try and think, I mean, you could do this exercise yourself. Look at the exterior algebra generated by two generators, psi n and psi n minus 1, and see if you can compute the kernel of gamma. And after a bit of playing around, you should come up with the following generators for that kernel. You can see, just sort of for dimension reasons, that it has to have dimension 2. Okay. But then you've got to then go further and on that kernel somehow figure out the kernel of the next set of gammas, the ones I'm drawing in blue here, that have to do with the second cut, and so on. Okay, so it would be nice to have some systematic way of understanding what you're doing by computing these kernels. And in fact, physicists do, and this is what these two states are what they call Bell states. So this is a well-studied, this is just notation, may not mean anything to you, but if you think about fermionic Fock spaces, this is the canonical notation for these states. So this exterior algebra is a Hilbert space, and this is how physicists would write these states. So these are exactly Bell states, which just means maximally entangled states. So this problem of these particular gammas that come up here are in fact well-studied objects in the theory of quantum error-correcting codes. So there are one set of gamma and gamma daggers for each one of these cuts, and in fact, this set of gamma and gamma daggers is basically a certain kind of stabilizer code. So I'll just, sorry for going over time, I'll just finish with this slide here. Okay, so theorem. The idempotent E, which is derived from these gamma and gamma daggers, which computes this composition in LG from the cut. So these x's here are standard operators in the quantum code world. So this is acting on C2 to the n-1. X is the operator that sends 0 to 1 and 1 to 0, acting on a single qubit. Xi means x acting on the ith qubit in this tensor product. So the idempotent which you get out of these Clifford operators for computing the composition from the cut is a well-known object. So this is the standard projector for what's called a stabilizer code. And the particular code is just these self-adjoint operators you see in that product. What that means is that a finite model for this composition is given by tensoring with the code space for that code. So that is the joint plus one eigenspace for these operators here. That's a particular class of entangled states that I could write down, but I think it just would require some notation and maybe not mean too much to you anyway. So this code is well known. It's sometimes called a quantum wire or a Majorana chain. It's very closely related to the Ising model, so it's a very standard example of a quantum error correcting code. So the upshot here is that we started by looking inside the composition in LG to see if there was extra structure there. We see that indeed you can identify extra structure based on Clifford algebra representations. And when you examine that structure in this very simple example, what you see is that it is exactly a quantum error correcting code. The process of going from the cut, finding this coefficient space to extract the finite rank representative for the composite is exactly the error correction process for this code. And I don't have time today, but there's an equivariant version of this where you use more interesting matrix factorizations, and that produces new examples of quantum error correcting codes. Well, we don't know what they correspond to, but That's what we're currently investigating as a method for producing new codes. So thanks for your attention. I'll stop there. Sorry for going over time.